Okay, so it started. So Manny, please introduce yourself. Everybody, I think most attendees know you very, very well. But in case there's new students or researchers who are not very familiar with your great work in the past, maybe you can give a very quick self-introduction.
Yeah, thank you for including my presentation today, Kai. Um, my name is Mani Venkatasubramanian, and I am a faculty in electrical engineering at Washington State University in Pullman, and I also serve as the director of our Energy Systems Innovation Center here at WSU, which manages the power program. And we have a long history of power engineering education and research here at WSU. And my research has been focused on power system dynamics, stability, and control um, uh, pretty much since my PhD dissertation work. And also, I have mostly been working with PMUs, how we can use PMUs for oscillation analysis and the tools that we have developed. Some of them have been adopted by vendors, and also some of the tools are used in control centers for oscillation monitoring. So today I am going to talk about a new tool that we have developed here, which is based on SCADA measurements. So this is different from what I normally work on. And the motivation for why we are looking at SCADA, and here are a couple of recent papers that I will be presenting today. This is the PhD dissertation work of my student Salman, who just graduated in fall 2025. And he is now happily working at SEL. This project, however, was sponsored by RTE in France through Power System Engineering Research Center, or PSERC. So we thank them for the support. Now, why look at SCADA? Um, Traditionally, PMUs have been used for oscillation monitoring, and in fact, oscillation monitoring is one of the primary success stories of why we need PMUs in the system. And lately, we have also started looking at synchronized waveform measurements for high frequency oscillations that are coming from uh, inverter based resources and power electronic converters. So, here, however, we are focusing, or we are looking at SCADA primarily because SCADA is readily available. Even today, many of the power utilities, the PMU coverage is low, especially when it comes to generators. And we know that oscillations, especially forced oscillations, can happen on any of these generators or from IBRs. And so we need better observability of the sources, potential sources in the system, and that's where SCADA really comes in handy. We have typically thousands or tens of thousands of SCADA measurements compared to hundreds of PMU measurements. And so that's the main motivation. But then again, the advantage of PMU, we know it is synchronized sampling and also at high speed, typically either 30 hertz or 60 hertz in this country. Even 120 hertz is now being discussed. So it seems appropriate for observing oscillations or analyzing oscillations using PMUs. On the other hand, SCADA scan rate is typically much slower. It may be as slow as 10 seconds, once in 10 seconds. Some of them have fast SCADA systems, maybe once in half a second, but still, these are significantly slower compared to PMU reporting rate. Then, how can we use SCADA for analyzing oscillations, because we know from sampling theorem, we need at least twice as fast as the oscillation that we are observing in terms of the scan rate to capture the information from the oscillation, in a theoretical sense. Whereas if we say 10-second SCADA rate, that is, roughly speaking, 0.1 hertz, so it would seem appropriate for only oscillations 0.05 hertz or slower. But we know the typical oscillations are much, much faster than that. Now, the trick is, and what helps the analysis, how we can use SCADA, is because the SCADA scan or SCADA polling is done in an asynchronous fashion. And they are not synchronized. And in fact, if you look at two consecutive SCADA measurements coming from the same RTU, the time gap between them will not be the same, because this is based on the polling schedule, how the RTE, how the RTU monitors or measures the signal and the communication delay between the RTU and the control center. So this is kind of random, and this is well known, and that's what we exploit in our method. So if we think of an oscillation, and I will show some pictures shortly, what we observe is the SCADA observation of that oscillation can fall anywhere on the waveform. So when we have an oscillation with a larger amplitude, then the SCADA will typically have few or more, depending on the amplitude, high energy signals compared to low energy. So anyway, I will hopefully illustrate this better with pictures soon. So that's the distinct feature that we can exploit in SCADA signals for analyzing oscillations. And this is something that we had observed earlier in a paper. What we contribute in the new research is how to make this rigorous, how we can use inferential statistics to develop rigorous tests where I can say with 95% confidence that there is an oscillation of this much amplitude, and how we can do this really in a reliable fashion. And I mentioned the earlier work. So this was back in 2017, and this was in collaboration with our friends at Peak Reliability. We developed two algorithms, and we wrote a paper back then. And this was also implemented in the control center at Peak Reliability, and it was tested for a couple of years. But unfortunately, Peak Reliability shut down. And then that was the end of that research at that time, and then we picked it up recently. And what we saw, the method SCADA-based approach has been used in industry. We saw a recent paper from the Indian Power Grid, and also it was reported by CAISO, California ISO, that they have used SCADA for oscillation analysis from IBRs, where PMUs were not available. So the thinking why this works, this is an actual field measured PMU data and the corresponding SCADA data from an RTU, which was present on the same bus, monitoring the same power signal. So this was one of those buses where we had both simultaneously a PMU measurement and a SCADA measurement for an archived event. And you can see that the SCADA indeed tracks the PMU pretty well. And also you can see the change in the nature of the SCADA signal as the oscillation begins. We can see this is becoming more and more noisy kind of a signal in the SCADA. And this is because, like I said, the SCADA measurement can land anywhere on the oscillation. And so we get this different pattern in the observation. And here is a zoomed in version of the same PMU and SCADA data after we have done some detrending. So now it's even more clear. You can see initially there is like an ambient part, where the SCADA also is kind of small in amplitude. And indeed, you can also get some noise kind of uh, high signals in SCADA data that we have to be careful about. Then when there is a smaller amplitude oscillation, you can see we are seeing some larger amplitude in the SCADA data, though it's not always the case because this is random sampling. You can have both low and high amplitude in the SCADA observation. Then when the amplitude increases, we are seeing more of those higher amplitude. And when the amplitude is even larger, we see that the SCADA is showing at least some of the observations have this higher amplitude. So that is the signature of what we see in the SCADA data during oscillations. And here we have shown for comparison the three different periods. One is the ambient, and now the thinking is if I put a band that I am looking for, say in this case, I want to know if the oscillations are more than 1 megawatt. This is just taken for illustration. Then clearly in the beginning, when it is just the ambient data, all of the SCADA observations stay within that band. So we say that we don't have any transitions between bands. Whereas when we have this small amplitude oscillation, some of the SCADA measurements end up outside of that band, a few of them. So in this case, there is potentially some kind of an oscillation which is just above 1 megawatt. Whereas when the oscillation amplitude is larger, you can see we get more of the SCADA measurements or SCADA observations outside of this band. So if I count the number of transitions between any two consecutive measurements, whether they stay in the same region or they go over from one region to another, that will give an indication whether we are having an oscillation or it's just ambient fluctuation. So that's the thinking. And one thing that we want to caution in using SCADA for this type of oscillation analysis, and that is some of the utilities include or implement uh, low pass filters or slow kind of smoothing filters in the SCADA before it comes to or after it comes to the control center. And unfortunately, something like that will kill this information that we are looking for. So if we don't have a low pass filter, this is what we get. And you can see that we get these observations outside the band. Whereas if we have a strong low pass filter, then now the oscillation amplitude has become much smaller. So in terms of the random sampling, then all of the samples stay within the band, and we can't really tell that there was an oscillation that was going on. So one assumption we make is there is no low pass filter, and the SCADA signal does show the signature of oscillations. And we have seen that many of the utilities, this is indeed the case. And for those who implement the low pass filters, we encourage not doing so because we get more information by using the unfiltered SCADA measurement rather than the filtered one. And so now I will briefly introduce the algorithm. What is the theory behind it, or what is the thinking behind it? So this is what I was talking about. Here we have taken um, an oscillation waveform, and I am assuming the oscillation or the SCADA scan rate is once in 10 seconds. And this basically then we will get one observation in every window. And where that point is, like I said, is asynchronous. So it may be anywhere within this window, depending on the polling schedule. And so we may get different snapshots or different landing on the signal depending on when that observation occurs. Now, what we are saying is if we can count the transitions. So for instance, between the first and the second, they both are in the top window. So we say there is no transition. And the third also, there is no transition. Whereas going from third to fourth, here we have a transition. Fourth to fifth, no transmission, no transition. And then here is one, there is none. Here is one more, and one more. So here, let me count. So we have 1, 2, 3, 4, 5 transitions out of a possible 9 that is possible, because here we have 10 SCADA observations. So there is a maximum of 9 transitions which can happen, but we have a count of 5. So how do we know this 5 is an acceptable number for counting this to be an oscillation event? Because we may have some noise related spike which pushes the signal outside, and we don't want that kind of false alarm or false detection. And so this is where we need the statistical theory. So we can assume, and here I'm just illustrating how this concept works. So we have taken 3 different waveforms with 3 different amplitudes, and I have fixed the band at plus minus 5 megawatt. And in the first one, the amplitude is 4. So all of the observations are within the band, there is no transition. So this would be the rejection that there is no oscillation event, at least event of interest, according to what we have specified as the threshold. And whereas when the amplitude becomes 8, now you can see in this particular sample, we have 5 transitions. And when I increase the amplitude to 16, I end up with 8 transitions. And this is because there is more of a probability that they end up in different regions when the amplitude is higher. But then again, because this is probabilistic, even if I take the same waveform and observe on different windows, we will get different transition numbers. So here we have 3 different random samples. And in the first case, we have 4 transitions, we have 5, and then, the third case, we got 6 transitions. But definitely, or there is a high probability that it won't be 0. Now, on the other hand, if the amplitude has become 16, and here again, I have taken 3 random samples, and you can see we are getting transition counts 7, 8, and 8. And these are higher than 4, 5, and 6 that we got for amplitude 8. And this is something that we can show theoretically or rigorously by going through analysis of probability. So if I take any kind of signal, and if I define these bands B minus B, and then we divide the region to R1, R2, and R3, and I assume that the signal that we are observing, which let's say is an oscillation, and this is an amplitude A, then we can assume the probability is uniform for convenience between A and minus A. And the question will be, how does this A compare with B, and what are the probabilities? And this is something that we can derive rigorously. And we can show that the relationship looks something like this, that if I assume a band of 50, and if I assume an amplitude A, what we can show is when the band or when the amplitude is less than 50, the probability is 0, probability of transition. Whereas the moment the amplitude becomes, say, 80 or higher, the transition probability is pretty much unchanged, or is more or less around this 0.6, and it stays that way over a large range. So this gives us the indication that if I look for whether the probability of transition is above certain threshold, I can tell whether the oscillation amplitude is above the band by a certain amount or not. And we can again make this rigorous because we have these individual observations. Each of them, either there is a transition or there is no transition. So it's a simple Bernoulli distribution. Then if I count the number over n of experiments, then the total number will be a binomial distribution. And since the SCADA measurements, there is no correlation between when the different or when consecutive samples occur. This is because of the asynchronous polling used in SCADA architecture. We can show that the experiments or the consecutive observations will be independent. And this helps formulate this problem nicely as a binomial distribution. And then we can calculate what will be the probability that a distribution or a certain count, the transition number will be 10 or 15. Each of them, we have precise formulas. And now I can set it up as a rigorous statistical test. We want to make sure that the transition, either there was a transition or there is no transition. And so, or I should say there was sufficient number of transition. And this is essentially what the test comes down to. I am skipping some of the theory here, but we can formulate a type 1 error, let us say 95% confidence, and then we can show that this will give us a number that the transition should be 12 or 15, depending on the number of total number of observations or total number of samples. So if I have 50 samples, then I can say if the number of transitions is more than 30, then we are 95% confident that an oscillation event of sufficient amplitude occurred in the experiment. And also in this case, we implemented both on the oscillation window and also for the ambient, because some of the SCADA signals will always be noisy. And those are not of interest to us. And we want to reject them from the analysis or from the hypothesis. So we apply the test as a reverse test or as a negative test for the ambient window. So just like the transition count should be above the threshold for oscillation window, the transition count should be less than threshold for the ambient window. That way we can rule out these false alarms that can happen. Now we can continue this analysis, and we can also find out what is the type 2 error using statistical theory, which is, so the type 1 error is the probability that we make a false oscillation event alarm when there is none present. So that we control by specifying the confidence threshold or the error, how long that or how large the tail should be. And typically we use 95%. But say if we want to make it 99% confident, then we will end up with a higher threshold for the transition number. And so we will be more conservative in classifying an event to be an oscillation. So on the other hand, if we set it too high, then there is a danger that we miss an oscillation event when it actually is present in the system. So this is, this can be analyzed by looking at what they call the type 2 error. And also one of the nice things here is typically we have 10 or more, say, measurements. In that case, the binomial distribution can be nicely approximated by central limit theorem, by the normal distribution. And this is beneficial because initially we made some assumptions on the probability being uniform and that the observations are independent. Whereas even if we have a different kind of a waveform, even if the waveform is, say, nonlinear, which is typical in forced oscillation, then it doesn't really matter because when we look at the overall binomial or overall distribution over n samples, then that becomes normal, and that we can approximate by using the central limit theorem And this is why this method is really robust with respect to the type of oscillation or any kind of correlation that may exist in the data. And in the paper, we show this with sensitivity studies, but I don't want to go through all of that here. So here is the type 2 error plot. And this is done for assuming the band is set at 50, and we have set the threshold assuming the 95% confidence. And now what we observe is if the oscillation amplitude is say 75 or 80 or above, then there is almost 0% probability that this is missed by the experiment. So we can be almost 100% confident that whenever there is an oscillation which has amplitude above 80, this method will detect or it will pass the statistical test. And for detrending, we have done two types of, or we test two types. The one is commonly used in statistics is just to take the difference between consecutive samples or first order differencing, and that is effective. Or we can also use a median filter that we had used earlier in our previous work. So we tested both and they both work well. So we typically do some data pre-processing and then the detrending. And we have tested this on many events that RTE experienced in the last 2 years. Typically, they would give us the data and with all the names hidden as a blind test. Then we will run it through the algorithm and then get back to them with which generator or which signal had the largest amplitude among all of the observations. And for the events that they gave us data for, this method correctly identified the source generator in all those cases. And now we have coded this and we have given the code to RTE, and now it's also been made open source. I'll show that a little later. But so for this event, for instance, this is from 2022. So we had 2,200 some odd signals in the data set. So among them, we wanted to find which one showed the largest oscillation. So what we did was we take some, because we don't know how much band or how much the amplitude to expect in a real event, we just start from some low value. So here we have shown when the band is 43, all of these signals pass the test, that there is a significant oscillation which had amplitude more than 43 megawatt. Then we raise that band, we make it more and more. And so some of the generators which don't have that much of an oscillation will start to drop out. Then when we have 83, we still had about 6 signals. And then when we go to 93, we didn't get any. So this means the oscillation amplitude maybe was just around 83, or, again, it depends on how aggressive or how conservative we set our probability test thresholds. But we still see there are several measurements that showed us a potential source in this event. And the reason we found out later from RTE that they have independent measurements of the same generator in the form of SCADA measurements. And this is done for redundancy, that for this generating plant, they had something like 4 or 5 different SCADA RTUs which were monitoring the same signal. So you can see this clearly. We have shown the SCADA plots and then the detrended plots, and you can see they look almost identical in terms of what we see in the SCADA data. And here is some more. But what is interesting, when we plot them together, so here in this picture or the plot, each dot corresponds to, or each color comes from a different RTU. So even though the plots overall look the same, if you look at any one sampling time or reporting time, you can see the values are different. And this is exactly the random nature that we talked about, because even though they observed the signal during the 10-second period, those RTUs landed on different points on the waveform, and indeed, their actual values are different. But what is interesting, statistically, they all have the same property. And this is indeed what we see by the visual observation. And this is why all three of them passed the statistical test, and they are flagged as the ones with the largest amplitude. So this was really a nice validation of the formulation that the SCADA observations are independent and they are random in even though they are all monitoring the same signal here. And then also for the same event, RTE gave us the transmission line data from all of the lines that are within the RTE footprint. And here we found something interesting as well, that the signals which start from this 1203, 1204, those are all near the generating plant. Whereas we saw there was one additional transmission line flow which was significant. And from the number, it looked to be different part of the system. And indeed, when RTE looked at the names or the numbers and correlated it with the actual transmission lines, we found out that one 444 happens to be a tie line flow, and that was between France and Spain. And the reason this gets flagged, which is far away from the source, so the source was located in the north of France, whereas the transmission line was in the south of France. And this is because during this event, this was a forced oscillation event, which excited the inter-area mode between France and Spain. And this is why the transmission line connecting France and Spain was showing significant oscillations. It was not a strong resonance event, it was weak resonance, but still, this analysis was able to provide some insight that this was a resonant event and not just a local event. And again, that was something that we learned by looking at the real data. And this is, again, one other potential use of this approach, that we can identify which transmission lines are showing what level of or what amplitude of oscillations by going through this analysis iteratively. And this is the tool that I mentioned. So we have now developed this framework into a Python coded a tool with some visualization. And it's as long as the data is available in CSV, this program can read the data. Then we can specify where the oscillation started, where it ended. Then it will go through all of the signals and then identify or rank which ones are the highest amplitude and the next so many that it detects by using this analysis. And this tool is now open source, not just the executable, but the code also. So all of it is available on GitHub. And here is the link I have provided at the bottom of the page. Next, I just wanted to briefly talk about anytime we have a practical algorithm, it's important to have multiple ways to test whether our information, our conclusion is correct or not. So for robustness, we developed a second algorithm that we call as the DOSA's algorithm. And here the thinking is similar but slightly different. So instead of looking for transitions, which we did in the previous approach, here we just want to see how many of the SCADA observations are above a preset band. So the thinking again is if it is just ambient kind of fluctuations, then none of the observations will exceed the threshold. Whereas if the amplitude becomes larger, we will see a few that go above that threshold. Whereas if the amplitude becomes really large, then most of the observations will be above the band. So we can just count how many of the observations or how many of the SCADA measurements are within the band or outside the band. And this can be used to uh, uh, tell whether there is an oscillation or there is no oscillation. So here again, we can develop the statistical or probability theory. And this is even simpler because the probability is, either it is in below the band, then we have the probability, and then if it is above. And what we can show is if A becomes really large, then the probability of being in band R2 will become nearly 1. And so here the plot of probability is more straightforward and it is easier to interpret. And this is why what we propose is this method can provide some direct insight on the amplitude of oscillation by using this approach. And here again, we can formulate it as a binomial distribution for the number of observations which are above the threshold. And then again, we can implement both for the oscillation window, ambient window, and the type 2 error is also uh, very strong for this method. Here, it goes to 0 slightly at higher amplitude value. So previously, for the other method, pretty much when the amplitude was above 80, when I set the threshold or the band at 50, we got nearly 0 type 2 error. Here it has to be slightly higher, about 110. Then this method is able to detect or not miss any oscillation. But then again, the band value, whether it is 50 or 20, that's up to us. We can say when we think an oscillation is important for analysis from either operator or engineer perspective. And here are some examples where we have tested this approach and we show that the method works well in finding this. And just to summarize the OSS method, we are looking for transitions that we don't want the SCADA measurement to be in any one band. It should be moving back and forth to signify an oscillation. Whereas in this case, we are not so much looking for transitions. It just means we want high amplitude. So this, intuitively, the first method is more tuned to oscillations, whereas the second method just means we are having some high amplitude in the observation. But because we have removed the trend, typically this DOSAS also works well for oscillation events. And then we have several examples, and this is an event from RTE, and then we also have some examples from the VEX system, and I will let you look at the paper for the examples. And like I said, it has been used by RTE engineers for the last 2-3 years because now they have the tool themselves. So they directly apply the test whenever they have an oscillation event. And this has been useful in finding the source. And also, this was recently used for analysis of the Iberian blackout. And that's something that we hope to write a paper sometime in the future, whenever they let us publish the results. Again, I should clarify, we don't have any of the data. The data is with RTE, and we just learn about how this method is being used. And so, in terms of future work, I would say that we need maybe even other methods which are based on SCADA that can be useful to provide some confidence in terms of multiple methods. And also, one a new approach that we are pursuing is previously we needed to know when the oscillation started or ended, and this was done by using PMU-based oscillation monitors. Whereas now we are trying to extend and see if we can directly find the oscillation evolution using SCADA data itself. This is challenging, but it is exciting if we can do that, because then that makes this method much more powerful. And one of the weaknesses I should have mentioned is because it is based on SCADA with slow sampling or slow reporting, we cannot determine or we cannot ascertain the frequency of oscillation. All we can say is there is an oscillation of this amplitude. Then we will still need PMU or DFR or some other faster signal to get information on the frequency itself. This method is all targeted towards the amplitude. And in a way, this goes beyond the sampling theorem, because we are using much slower sampling or reporting frequency, but we are still able to estimate some features of the oscillations, not all. So that's where the sampling theorem still is, we are not questioning, or, we have to be within the framework of the sampling theorem, and that's where we pay the price, that we cannot measure the frequency. So I will stop there, and I am looking forward to any questions you may have.